Okay, did you give this a try? I hope you tried to find out which ones were localized versus delocalized and the hybridization. Let's go through them. Color-coded them. Hopefully that'll make it clear. So I'm starting with this one, localized. That means I can't do any resonance with it. It's a lone pair that's not next to a pi bond, right? Or an open octet. It's far away from even the rest of the molecule. So there's 4 electron groups on this nitrogen. So it's got to be sp3 hybridized, which means all electron lone pairs or bonding pairs are in sp3 hybrid orbitals. So that lone pair is in an sp3 hybrid orbital. This one is a lone pair that's not allylic. It's on a nitrogen that's in a pi bond, not next to a pi bond, in a pi bond. So it's localized. That's not one of our resonance patterns, is for it to, not for it to be in a pi bond, it's for it to be adjacent, like this one is, but we'll get to that one last, because that's going to be a what scenario, right? So localized. Localized means it doesn't have any resonance. Why are we doing this? Because resonance is going to change your answer. But since it has no resonance, it won't change your answer. So that's why we're doing this first. So you should get that because this nitrogen used a p orbital for a pi bond, one of those p orbitals is gone, right? So in other words, if you make your list, S, P, 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 a p orbital was, pi bond was made, p orbital was used, must be sp2. That means everything else that's not part of that pi bond is sp2, including the lone pair. So that lone pair is an sp2 hybrid orbital. That blue one is delocalized. It's an allylic lone pair. Let's push the electrons. Do you have any colors left I haven't used? I'll do red, even though I've used it already. I could push it 2 ways, actually. I could push it here or here. So the yellow for this way. So it's delocalized. Why does that change everything? Well, first of all, you wouldn't probably have guessed that that lone pair was in a p orbital, because we're not making a pi bond with a lone pair at first glance. We actually are. Let's draw the resonance structure. Hence the question, is it delocalized? When we draw the resonance structure, so let's do I'm going to undo my yellow arrows. Let's do the red path first, because don't worry, I will account for the yellow ones later. All right, so new pi bond. So I'm telling the story of these arrows. Negative charge, lone pair still there, and H2. All right, look what I did there. I made a worse resonance contributor, but I illustrated resonance. Cannot deny that it's there. I could also have gone the other way, which will account for that yellow path. Send these back home. I forgot about this pi bond still there. Send these back home, back to here, and let them land there this time. I hope you've been practicing your resonance. That will pay off, because I'm not moving at a snail's pace with resonance anymore. And it's going to only get faster. Lone pair landed there. I accidentally drew an extra carbon, so let's make up for that there, and H2. That one's back to normal. This one still has a positive. So notice my analysis. Step back away and I say, okay, I have a net neutral, because I started off neutral. My resonance structures look pretty good. What else do I notice? I notice that the nitrogen in question in all resonance contributors makes a pi bond. How does it make a pi bond without a p orbital? So you might have wanted to say, if you went away and assigned hybridization to this, say, hey, it has 1, 2, 3, 4 electron groups. It's sp3. with no p orbital left over for pi bonds. That's impossible if these resonance structures are possible. You have to have a p orbital for these to happen. So because it's delocalized, we cannot have it be sp3. So when you see a lone pair, this is a very important exception to the way we assigned it previously. You see a delocalized lone pair, make sure you find out if it's using a p orbital. If it's using a p orbital, it's in a p orbital. It needed the p orbital to make that pi bond, right? Look what it did. Those arrows literally said they're making a pi bond. Therefore, that lone pair is in a p orbital. Yes, it's higher energy than a hybrid orbital, but it's worth it because it allows for resonance. So the right answer is that this lone pair is in a p orbital because it's delocalized. Watch out for that. Delocalized electrons and hybridization. Let's compare that to a scenario where that would not have happened. I can just make a small change to the structure of histamine. And let's assign the hybridization of, actually instead of assigning the hybridization, which I'm going to do something similar, tell me what orbital each of those lone pairs are in. And we'll do it in blue again. Blue versus red versus green. Well, you should already say red and green are going to stay the same because they've always been localized and they're still localized. So, except for the fact that did I take away a pi bond? I took away a pi bond. So I actually changed red. So green stayed the same, sp3. Let's look at red. Red has 4 electron groups, no pi bond this time. So I did change it, and I'll leave it alone because I need to change it. So red and green are the same idea. They have 4 electron groups, no pi bonds nearby. None, so no p orbitals being used at all. So now this one's sp3. Now look at the blue. Is this delocalized? No, there's no way for the lone pair to move. There's no pi bonds, open octets, or anything. So this is also sp3. So if the question was what orbital is holding that lone pair, your answer is it's in an sp3 hybrid orbital. If I say what orbital is holding that lone pair, your answer is it's in a p orbital. Simply because it's delocalized versus localized. Redo that one on your own. That's a tough concept, and all the old exams have at least one problem like that. Go look at those too, because that takes some time, and the homework has a lot of those too. So that's something to emphasize. We're going to end on a light note. I want to review the bond lengths and strengths. I think that last one was a light note because it's actually a fun, interesting concept. But this is simple because it's just a consequence of what's going on in terms of trends. So when we have a difference in hybridization, so notice, let's write this down. Single bond only versus a pi bond versus 2 pi bonds, the bond gets shorter. What do we mean by shorter? We're talking angstrom scale here. So it's about 1.2 angstroms, and you're going to see this number a lot. A CC carbon single bond is about 1.54 angstroms. So this is longer. And because of that, longer bonds are usually weaker, and shorter bonds are usually stronger, harder to break. So you're going to see the trend hold true with something that's hybrid, even if we have like a hydrogen, which is always an S, bound to something with different hybridization. So an sp hybridized carbon, for example, has more S character, more chocolatey, right? So it has a shorter bond. This one has a longer bond. Therefore, this is weaker, much stronger. Okay, the last one I want you to be kind of comfortable with trend-wise. Look at the halogens attached to a carbon. What's the difference? The size, right? That's periodic trend there. What's the difference in their size? Well, I think I have this example here. I don't have it right here. Iodine is larger, so it needs more space. It's going to be farther from carbon, so that's going to be a longer bond. So that means it's going to be weaker. Okay, just a few other little things just in case you're not familiar with angstroms. 1 angstrom is 10 to the minus 10 meters. So an angstrom's our unit for bond lengths. These over here have a relationship with what's called S character. So notice that when we have more S character, the bond is shorter. Notice that phrase I'm using, S character. So S, well, we're going to see this a lot. Something with more S character does this or does that. Shorter bond, stronger bond, more acidic, less acidic, affects its reactivity in some way. So it's good to straighten that out now. What does that mean? More S character. It means what you might think it means. It means that if it's hybridized to include S, which it always will, if it has more percentage S, like SP versus SP2 versus S, and remember S was the chocolate. Which one was the chocolatiest? The SP, right? Because you only diluted it with a little milk. That had the most S character. But how much was it diluted by? So we took a full glass of chocolate, pure chocolate syrup, full milk. And then it was 50-50, right? One S, one P, that's 50-50. But if you had to split it among 3 glasses like we did, it was 33% S character. And then finally, this one would have 25% S character. Right, so this region is where we have increased S character. It usually indicates stronger or more tasty if it's chocolate milk.